Okay, so welcome everyone again to another Friday, another quantum hardware course. Today I'm just planning to make some exercises that we have in the new Symphony book and discuss a little bit to organize the theory that we studied so far, and then the next Friday we keep going with another theoretical part. So let me share my screen. I have no slides today, so we will use directly the whiteboard. So, okay, let me close this. Okay, so the exercises, they are here in the new Symphony book. I will not like to write the same thing, okay? Just we read here, and I put the the reference. What this? What that pattern is related to, or it's about the
No, no,
airplane.
it's the ancient computer. I think it's
Oh,
called
okay.
ancient Ikeros, if anyone wants to have a look. So
So okay, I'll check in the end. So okay, let's see again where it is. Okay, this is the theory. It's finding here. Phase shifters exercise. So we see some exercises. They are simple, but it's good because they have some like circuits that we can like apply our theory, and in the end, you guys will understand because remember that we are planning to give some certificates, and the idea is uh, you guys like who wants the certificate try to develop some circuit that you have like your algorithm in Python. What's the corresponding circuit for this algorithm? So we see some examples here during the course, and in the end, this could be like a nice project to have to have a certificate. So okay, so just like remember what we did, the main results. Like so today is like remember that we study the splitters and phase shifters so far, and we saw the quantum properties of these guys. So phase shifters. Okay, we saw like that we could represent quantically phase shifters using the Hamiltonian of this type. That's called HP to be. The Hamiltonian we define in terms of the index of refraction related to this is the vacuum and this is the medium times the zeta operator, the zeta Pauli matrix. And we have defined P operator, like the operator related to the phase shifters, in terms of this Hamiltonian, like this, minus A H P L over C0. And L is the size of the shifter, the Z. Yeah. And C0 is the speed of light. Speed light in vacuum. Okay, and we saw that we could represent P in terms of exponential of a matrix related to some phase that we call just cap delta 0 exponential delta delta or delta over 2 has no really difference. He uses in the book over 2 because you want to relate with the Z rotation gate, right? Okay, and this is just to we remember what we saw. And one application is here in exercise what's the number? Exercise 7.7. Well, here I'm not to write everything. So let's just read here in the book this exercise. So he asks us to show that the circuit below, like this circuit, transform a dual railway state by this matrix. So if you take the top Y to represent 0, 1 modes, and the bottom by 1, 0, and this box represents a phase shift by pi. So okay, this is just observation. So note that this such optical circuit propagation in space is explicitly represented by putting in lumped circuit elements such as in the above to represent phase evolution. In the dual rail representation, evolution according to 720 changes the logical state only by an unobservable global phase, and thus we are free to disregard it and keep only relative phase shifts. 720, 720. Oh, it's the definition of the Hamiltonian, right? The free space. Okay, but he wants us to show that this circuit we could represent like in the dual rail representation by a matrix of this phase, and it's simple. Let's do it. So he says that in the top wire, we have a phase shifter that shifts by pi, and in the bottom wire we have nothing, just the wire. So here he defines psi in, and here psi out. The input and the output. Okay, so if we want like to, oh, and he say that here in the top, I have the state 0, 1, and in the bottom, the state 1, 0 in the dual rail representation. So okay, so the psi, we could like define like the psi out in the top is just the application, the phase shifter to the 0, 1. But remember that we did in one of the classes, we know that P applied to the state 0, just give the state 0, do nothing. But makes sense because this state here is like the vacuum. It means there is no photons coming. So if no photon is coming, the phase shifter will not do nothing. And when I have one photon, one single photon, P applied to this single photon, we did this using this representation. P just give like exponential I theta 1. So when I have P applied to 0, 1, so remember this, just people that not use it, the notation is this. So P applied to 0, do nothing. P applied to 1 as the phase, to the photon. So this gives you this state. And in the bottom, nothing happened. See out is just 1, 0 applied to identity, right? In the bottom. And the total psi is just psi in the bottom, the top, plus psi in the bottom. And this will give pi 0, 1 plus 1, 0. And these guys we define as our logical gates. So this 0, 1, in case my logical 0, and the state 1, 0 is my logical 1. So my psi out is just it could represent like a matrix exponential I. In fact, this delta is pi, right? Delta equal to pi. But delta, because this is the 0, 0, 0 is this, 0, 1 is 0, and 1, 0 is this state here. 0, when I say 1, 0, is 1, 0 logically, right? The blue. And 1, 1 is this here. This one. So this is my P. And this is my psi in. Psi. That's my state initially, right? It's here in the figure. This is the psi. Psi, no? Two states. Okay. What's the equation? Okay, and for delta equal to pi, that's the case we are considering. Psi out is just exponential I pi 0, 0, 1 psi. It's the equation 722. Okay, simple. Just an application of the theory that we discussed. Okay, and they have another exercise here. And this other we did in the class, very in one of the lectures, the second. That's to show the 7.8, show that P alpha can be expressed in this way. So we did this very similar when we were studying like the coherent states. I'll leave as homework, okay? 7.8. So homework, if you have any doubt, we can discuss in the next lecture. So exercise 7.8, homework. But to take the notes that we had during the when we were like discussing the coherent states, you see that it is very similar, the thing that he is asking. The thing is that the Nielsen Schwang, they didn't discuss too much like the coherent state. So they put this exercise to the students like see more details. So, but we did this before the exercise. So, okay. So this is the two exercises they have about phase shifters, only phase shifters. And we also discuss more interesting things about beam splitters. So let's just remember the things we discussed. About beam splitters. Questions? Let's check the chat. Yeah, yeah. Because in the book he just asked to prove that. So I believe is actually is in the book this expression. But yeah, this is -1. So he wanted to put here. So it's equation 723. Yeah? So okay. So now about beam splitters. Just to remember, we have like a brief discussion in I think in the last lecture or in the 2 weeks ago. Like classically, like the classical beam splitters, we know this type of behavior here. If I have like a beam splitter, if I send a beam of mode, let's say mode B, like a single photon, for instance, this photon could come here in the beam splitter and could be transmitted or could be reflected. If it's a 50-50 beam splitter, so it's 50% of these things happens. And it could also come, the income photon could come from the mode A, and it could be transmitted the same way. Transmitted. It could be transmitted, or it could be reflected. Again, 50% if you're being split is a 50-50. So this is the classical description. We are interested in the quantum properties. So in the quantum, we saw the last lecture, like if I have a, a beam come here, let's say a single photon, it could come, it's better represented with the jaw that is in the Nielsen-Schwarm book. It could come from the mode B, and the photon could be like transmitted, or it could be reflected. It could be reflected. If this happens, so here's the mode B. So I represent this photon by the cat1 in mode B times state 0 in mode A, where A is this mode. Times. So this would be the representation. And here you have my output. I should call B prime and here A prime. But also this could have come, the photon could have come here in mode A. If this is the case, so again, it could be like transmitted or reflected, I said. If it come in mode A, so the mode B is B empty times mode A with one single photon. And we saw in the last lecture, we could represent like the beam splitter operator called B. We could represent by this matrix sine of theta minus sine of theta sine theta cosine. So doing this in a 50-50 beam splitter, if theta is pi over 4, we could have like the B prime would be a superposition of these two states. So state 0, 1 plus 1, 0. And the same here would be a superposition of the two states. If you use, like here's the B splitter operator, here's my B splitter. That's called B. If you use this operator here, this matrix representation for B. So what we have, or what the beam splitter is doing here, if the photon is coming in one of this way, it put in a superposition of this way. So the beam splitter has this property to put in superposition that you guys can recognize. It looks like it's very similar with Hadamard game. And we'll see this in an example. So, okay, so this is just to remember the theory. And let's do some application. Let's see. Exercise. This 7.9. exactly like to show that this type of circuit like this could represent like a Hadamard gate. So when in Python you are doing some make your algorithm and you put the Hadamard gate in one of the the programs you are using, if you send to a quantum computing, this quantum computing is using like optical devices, you probably will have something like this, like a beam splitter and this a phase shifter, and you see that now that this is similar to a Hadamard gate. So exercise 7.9 show that the following circuit acts as a Hadamard gate on the dual rail single photon states, and that is on this thing up to overall phase. That's the phase. So let's do exercise 7.9. Exercise 7.9. It's the optical Hadamard gate. Okay, let me draw the circuit here. This is the circuit. And here I have phase shift by a phase pi. And here nothing. So we can divide this here. This is my beam splitter, and this is my phase shifter.
Question from Mohammed Reza. So have all of the gates implementations the universal set being discovered in the photonic case?
I think so. I think so. Since they can like make some hardware using the photonic case. So I think it's possible. Yeah. So okay, this answer the question of. So okay, just to remember, the beam splitter operator is this, and the P phase shifter operator is just alright, like when it's pi here, the phase, which is -1, but it's writing this way. So this is equation 735, and this is equation 722. So okay, this circuit we could like just like use this, but let's do this way. So the circuit here is just the product of B and P. So it's simple, right? Cosine minus sine, sine cosine times this exponential I pi 0, 0, 1. And this multiplication will just give you exponential I pi cosine minus sine, okay, exponential I pi sine and cosine theta. Okay, and if you want to write this as a Hadamard, we could like write the circuit. We could like, yeah, for theta equal to pi over 4, right? So this would give 1 square root of 2 exponential I pi minus 1 and 1. Or we could like exponential I pi 1, 1 minus I pi exponential minus I pi. And this now is minus 1, right? Exponential minus I pi. So I pi square root of 2. This is minus 1. So it's 1, 1, 1, and minus 1, which is the Hadamard gate. So exponential I pi times Hadamard. So remember, this is Hadamard. 1 minus 1. This is what he's asking, right? To show that this circuit. So if I have one B splitter and one phase shifter, I could have like a Hadamard, or in this case, it's a phase, so just a phase and it doesn't make difference. This in the end is minus Hadamard. The sign is not important. So we could have here the representation, optical representation for Hadamard gate. Okay, simple circuit. And the next is exercise 7.10, the Marzender interferometer. I will again just read and then we hit play. But this example is good because they use like beam splitters and phase shifters. Interferometers are optical tools used to measure small phase shifts, which are constructed from two beam splitters. The basic principle of operation can be understood by this simple exercise. So let's see. First, note that this circuit performs the identity operator. So this, which is the beam splitter, and this is the equivalent of the B dagger. That's why they put in the draw representation this dot here. And the second, they want to compute the rotation operation on dual railway states, which this circuit performs as a function of the phase shift P. So, okay, let's do it. So, exercise 7.10, the Ma, Zender, interferometer. So okay, so the first they want us to see that this circuit represent identity operation. This, that, this. So you could use matrix multiplication, but I think it's simple. We using the things that we already know. Like if I have the input here B and the out in the input in the other mode A, I would have here a B1 and A1. And you know that when we apply like the first B, first operator cap B, and here's B dagger. When we apply this B1, that's the output, will be just the sum for a 50-50 beam splitter, right? 50-50. Which means that theta T over 4. So when we apply B, cap B, we'll have the output B1 will be just B minus A square root of 2. And A1 is B plus A square root of 2. So this is my output here, but will be the input in the B dagger. So when I apply this to B dagger, this is my input. In my output, I'll call B2, A2. And just use the definition that we saw before, like the B2 will be B1 plus A1, because I the opposite, so we change the sign. So it's B1 plus A1 square root of 2. And that's the input, but this input in terms of the first input here, you just give like B1, B minus A, plus A1, that's B, plus A is over 2, right? Yep, we have square root of 2 here, in square root of 2 that comes from here, over 2. So this will give 2B or B. That's the first. B2 equal to B. And the same we could see for A2. A2 would give A1 minus B1 is square root of 2, which gives, just a moment, stop here a little bit. Let's see here. Just a moment, please. Okay, sorry, I'm back. Had some problems. But okay. Sorry about that. So okay, A2. Okay, now we use A1 and B1. So it's simple, right? The same thing. A1 is B plus A minus B1 will be B plus over 2, which gives A. Okay? So it means that it's the identity, right? Because my input is equal to my output. So we have the identity. So we have the circuit above represent the identity. The circuit above represents the identity operation. Identity operation. Okay. And the second part of the problem, they ask us to compute the rotation operation on the dual railway states for this circuit. Let me draw the circuit. So it's basically the same, but they put like a phase shifter. So it's simple as well. But the thing is that this could represent like a interferometer, like a Mazender interferometer. Is P, the phase, just on the top, B double. So again, we could like separate. I have here a B. Here is a P operation. And here B again. My output, I call B, my small b and A. My input, sorry, B and A. And the output, I'll call B2, A2. So, okay. To do this, again, if in the first part of the circuit, we could like apply B. We could multiply matrices, but I think it's more practical to use this way. So B, remember this is B1. be A1. So B1 is just B minus A square root of 2 for 50-50 being splitter. And A1 is A plus B square root of 2. So this is the first part. We'll do that. The second part, B, we know that the effect is just to put a phase. So B1 would come here. We call here B1 prime, and here is A1. So this B1 prime, we just have a phase. B1, because we are considering like a dual rail representation. So this would come like something like this way or this way. And when P is applied to this or that, the result will be just a phase. Okay? Oh, sorry, 1, 0. So this is my B prime. That's this guy, B1 prime. And A1 prime is just A1. So this A1 prime, this is the identity here, it's just A1. So, okay, and this is my third part of the circle. That's when I apply B dagger. On the third part, so I have B2 will give me like A prime. And the sign now changed because it's B dagger. So this was B minus A, now is plus square root. And yeah, I could write this. I think it's better we finished. We could write this in this way. So A prime is A1, and A1 is this way. So A plus B, that's A1. And B1 prime is exponential I phi B1, that's this way. So B minus A over 2, right? Because this is square root and this is square root. So we could develop this and we could find, if we put like B and A in evidence, we could find that this is 1 plus exponential I phi B plus 1 exponential I phi A minus 1 minus over 2. And we could write this in terms of cosine and sine. Just put the exponential in evidence. Exponential I phi over 2. This is I minus I phi over 2 plus exponential I phi over 2 times B plus exponential I phi over 2 exponential minus I phi over 2 minus exponential I phi over 2 times A. All this divided by 2. And now we could write this in terms of the sine of cosine and cosine. So B2 is exponential, this exponential I5 over 2. This is cosine, divide by 2. So cosine I over 2 B plus in fact minus, because if this is a sine, so I need to put this minus outside. So it's minus exponential I5 over 2 I sine of I over 2a. And in the end, we have the output B2 will give exponential I5 over 2 B cosine phi over 2 minus I A sine phi over 2. This is B. And the same if you use for A, we do the same thing. Just to remember here, A now will be A1 minus B1. And we just make the substitutions that we have here in the same procedure, and we find that A, in this case A2, is the output. You'll have this. It's the same calculation. A cosine phi over 2 minus IB sine phi over 2. So we could represent A, could write like B2, my output, in terms of my input B and A, my output A2, in terms of my input A and B. If I do that, I can write this in terms of matrix, like A2, B2, exponential I5 over 2, cosine I over 2, minus I sine over 2, minus I sine phi over 2, sine phi over 2. This multiplied by A and B, the inputs. And this is my circuit, what my circuit is doing. And this is equivalent if we see equation 4.4. This is equivalent to a rotation in the x direction, apart one phase. It's cosine. This is equation 4.4, okay? Just to remind, cosine of theta is this minus I sine theta minus I theta over 2 cosine theta over 2. This is a rotation, so what my circuit do, apart one phase, is make a rotation in the x direction. Okay, and remember that when we were like study only beam splitters, we saw that, let's see if I have the expression here. we saw that the beam splitter represent beam splitter would represent like the B operator. This cosine minus sine, sine, cosine. It would represent a rotation along the y component. And the phase shift would represent a rotation, only the phase shift alone would represent a rotation along the z component. That's this. And we have the mix of two. We have a rotation in the x direction. So okay, that's the the exercises where we have like some circuits. Let's see. Yeah, he wants like to show compute the rotation operation on dual railway states which this circuit performs a function of phase shift p. And this represents a rotation in the x direction. So imagine this interferometer. So all these others, like things that we already did, the calculation that we already did in the classes, I'll leave as homework, okay? 7.11 and 7.12. When we see the development of the theory, the difference that here he is considering a state with two photons, but we did a lot of these calculations with one photon, so it's basically the same. And here he did not specify the number of photons, but if you use this hint here, you see that it's simple. It's the things that we already did. So I like try to show these examples because I mean it's like a very nice application of the things that we study, the theory that we studied before. And as I told in the beginning, I think from people that want some certificates, this type of project I think would be interesting. Like you have like an algorithm, a simple algorithm in Python. You have the result and try to see the same result, but now using the hardware with the theory that we have here. And you should like have the same result that we found in your code. But now using the theory, like using the hardware, what's the hardware is doing. I think is a good idea for a project. But we see more when we are studying, like in the next, we see the theory about this nonlinear media, and in the exercise we have like some others like circuits that we can discuss as well. I mean, other examples like this one, and so on. And another interesting thing, but I think it's because it's simple, that you see the relation of beam splitters, quantum beam splitters with Lie groups. So you guys could just read this thing here, because the calculations is the things that we already did during the theory. So just read through this box 7.3. We basically make all this. There's nothing really new here. I mean, in terms of calculation. So you guys could read and have the same conclusions that we have. It's interesting to see that like application of Lie groups in this case for quantum hardwares, more specifically in quantum beam splitters. So a little bit short today. I'll try to be like make shorter lectures. So if you guys has some questions, Muhammad Riza had a question here. Also, do we know whether those gate designs exclusively use just beam splitters and phase shifters? I think this is example show, right? Answer your question, Muhammad Riza. So, okay. So I think we could stop today if you guys has no questions. And next Friday we return with the theory, now using studying like nonlinear devices, and we see applications. Okay, George.
Thank you, Carlos.
Okay, thanks. Welcome. So I will stop recording now. Stop presentation. And stop recording. So see you guys from YouTube next Friday to another section where we'll develop more theory. Today was just applications. So